Now for this part of the question, we're told that the traffic officer records 12 vehicles passing the fixed point in a 15-second interval. And we've got to state our hypothesis clearly and using a 5% level of significance test whether or not the traffic officer has sufficient evidence to switch on the speed restrictions. Now what I've done here is I've first of all defined our random variable x as being the number of vehicles passing in a 15-second interval, where x is distributed as a Poisson with a mean of lambda. Now we've got to test that mean value out. In a 15-second interval, if we are getting 36 vehicles every minute, then a 15-second interval is going to be a quarter of that time. So a quarter of the vehicles should pass through. A quarter of 36 is 9. So that's our starting point. We have our null hypothesis HO as being that lambda, the mean, equals 9. Now we're told that this traffic officer records seeing 12 vehicles pass the fixed point in this interval. So that officer observes 12 vehicles. So I'm going to say that my observed value, little x here, is 12. Now clearly that suggests that since we only expect 9 vehicles every 15 seconds, seeing 12 would make us think that the mean has now increased. So that is the alternative hypothesis H1, that lambda is now greater than 9. And the level of significance that we're testing is 5%. So I'm going to say alpha for that level of significance is 5%, or obviously as a decimal 0.05. Now when we're testing this, okay, just draw you a little diagram as I normally always do on these kind of questions. A number line here. Our random variable x can go from 0 right the way up to technically infinity, but it's not going to be that. But essentially there's no limit, okay, to how many vehicles could pass this in 15 seconds. But we generally expect to see around about 9. And so because we expect to see round about 9, I'm just going to put a section like that, okay? Now this is going to be fairly common to see this. So if this is what we expect to see when we are having lambda, the mean is 9, then we'll have this as a cutoff point here. This is where we would accept HO. We'd accept HO that the mean is 9, and once we pass this value here, this value is what we call our critical value. We'll call it R. Then once we pass that value, this is the point where it's going to be that we would reject HO. Okay, so we'll just put that down there as reject HO. So how am I going to figure out whether we accept HO or we reject it? Well, there's two ways that we can do this. Now one method is that we would reject HO if the probability that x, our random variable x, number of vehicles passing in 15 seconds, is greater than or equal to this critical value R, where we accept that lambda equals 9, the null hypothesis is true, in other words, turns out to have a value of less than 5% or 0.05. The second method, we'll just number this 1, okay, as the first method. The second method is that we would reject HO if the probability that x is greater than or equal to our observed value of 12, given that the null hypothesis is true, that is lambda equals 9, the mean is 9, turns out to be less than 5%, 0.05. That's our second method. Okay, so we'll go through these let's start with method 1. Okay, so we'll have method 1 here. So we'll start with this now, and we've got the probability that x is greater than or equal to r, given that lambda equals 9, is less than 0.05. Now if that's the case, then I'm going to be wanting to use the cumulative Poisson distribution tables. And so I need to look at probabilities that are less than or equal to a given value. So I can say that this is the same as 1 minus the probability that x is less than or equal to, and we've got to be careful here, it's going to be r minus 1. Imagine if this was some integer like 10. The probability of x is being greater than or equal to 10 would be the same as 1 minus the probability that x is less than or equal to 9. So we'd have to subtract 1 from this value. Anyway, this is given that the null hypothesis is true, that's lambda, the mean is 9. And that's got to be less than 0.05. Now if we rearrange this inequality, add this probability to both sides and subtract the 0.05 from both sides, then we'd have the probability that x is less than or equal to r minus 1, given that lambda equals 9, would be greater than 1 minus 0.05. In other words, 0.95. Now it's at this point that we would want to use the tables. And if we just bring up a section of the tables that I've just copied here. These are the cumulative Poisson distribution tables. Look for lambda, the mean equaling 9, and you should see some values down here, observed values. Now when lambda equals 9, we're looking for a value down this column which just beats 0.95. So you'll see it's this one here, okay, 0.9585, and it occurs at 14. So what we're saying is that from tables, just write this in, from tables we see that r minus 1 must be a value greater than or equal to the 14. So if we add 1 to both sides, we therefore got that r must be greater than or equal to 15. Now our observed value was 12, and clearly that's not greater than 15. Our cutoff point is 15 here. So 12 is going to be one of these kind of expected values, fairly close to the mean here, 9. So we can expect some fluctuation, but that's well within acceptable values. Okay, so we're going to accept HO. So I would say that since 12 is less than 15, we would accept the null hypothesis HO. So therefore we've not got a significant result, not significant. So the mean is going to be 9. Now I did say we'll do both methods, so I'll run through method 2 as well. You're going to need this at times. In fact, you're going to need this kind of method when we do the next part of this question. So for method 2, I'm going to start off with what we've got here. Okay, the probability that x is greater than or equal to 12, given the null hypothesis is true, then that the mean is 9. Now to work something like this out, okay, we would have to do 1 minus the probability that x is less than or equal to 11, given that the mean is 9. And we can use the tables above here, because the probability of being less than or equal to 11 when lambda equals 9 is this value here, 0.8030. So we've got 1 minus 0.8030. And if you work that out, you end up with 0.1970. And when we compare this to 5%, we can see that this is greater than 5%, greater than 0.05. So we did say that we would reject HO if the probability of getting 12 or more was very small. It was in this region here, less than 5%, but clearly it's not. So therefore we can expect 12 to be over here somewhere. So we can accept HO. So just to wind this up, we can say that accept HO, okay? And it's not significant. So either way, obviously you're going to end up, or should end up, with the same result. So there we go, method 1, method 2. Leave it up to you to decide which one you think is the easier, and then just go with it, okay? Either will do.